Find dy dx for the cardioid r equals 1 minus cosine of theta in terms of theta. So our first step is to let r equal some function of theta, f of theta, which gives us f of theta equals 1 minus cosine of theta. Since we have f of theta, we can now find f prime of theta. So the derivative of 1 minus cosine of theta is simply sine of theta. Earlier we determined that the derivative, the slope of the cardioid, or any polar function in general, is dy dx equals f of theta times cosine of theta plus f prime of theta times sine of theta all over f prime of theta cosine theta minus f of theta sine of theta. So because we have both f of theta and f prime of theta, it's just a matter of substituting in all the equations. Substituting in f of theta and f prime of theta gives us the quantity 1 minus cosine theta times cosine theta plus sine of theta times sine of theta all over sine of theta cosine theta minus the quantity 1 minus cosine of theta times sine of theta. Simplifying out our equation, we get dy dx equals cosine of theta minus cosine squared of theta plus sine squared of theta all over 2 sine theta cosine theta minus sine of theta. This is an alternative approach which we use x equal r cosine theta and y equals r sine theta, and we substitute in f of theta in for r and solve for it via parametric equations. The answer comes out to be the same, but the steps take longer and may or may not be as time efficient.